In the last video, we finished up by looking at this example where we had an archer who was trying to shoot an arrow for distance, shot the arrow at 60 meters per second, 30 degrees above the horizontal. Neglecting air resistance, we figured out that the arrow landed 318 meters downrange. Now here I have actually worked out what the x and y components of the initial velocity were. And I want to focus on the fact that the initial component of the initial horizontal component was 51 meters per second. And that's because I want to put to you a question. Let's imagine that at the exact time that the archer shot the arrow, that somebody in a very fast car was going down the road at exactly 51 meters per second, passing the archer and driving parallel to it. So that's a little, a bit over 100 miles an hour, so plausible. And we'll assume it's a closed course and professional driver and all that. Now, if somebody were to look out the window of the car at the arrow, what would they see the motion of the arrow as? So pause the video and get back with me on that. Yeah, if they were just to look straight out the window of the car, what they would see is they would just see the arrow go up and right back down. They would never see its x-coordinate change, and this is because there was no acceleration along the component of acceleration along the x direction. So that horizontal velocity is always 51 meters per second. So if a car is driving by at 51 meters per second and they look out the window, hopefully a passenger and not the driver, they would just see the arrow go straight up and straight down. And you might ask, well, who's right in making the observation? It turns out that the way the laws of physics work, both the archer and a passenger in the car are equally entitled to say that they are in what's called an inertial frame. And we'll talk about that more when we talk about Newton's first law of motion. Each person is equally entitled to say that they are an observer that is sitting still and that the whole rest of the world is moving around them. So the archer can say that they're standing still and the arrow is going downrange at 51 meters per second for a shade over 6 seconds before it hit the ground. Okay. And the person in the car can say that the arrow went straight up and straight down for a shade over 6 seconds. And each of them can translate to what the other one sees. The archer can translate to what the driver sees by saying, well, the arrow is going at 51 meters per second downrange, and so is the car. So it would make sense that an observer in the car looking out the window, they'd never see the arrow go in front or behind of the car. It'd be just like another car going down the road at 51 meters per second. They would see it go up and down, but they wouldn't see any right and left action. And while it may seem counterintuitive, the observer in the car can say exactly the same thing. What the observer in the car would say is that the archer is moving backwards at 51 meters per second. Now this may seem silly, but if you've ever driven down some really long, really straight stretch of road, you can get yourself into a zone where it really feels like your car is stationary and the whole rest of the world is moving around you. But you know what? There are literally no experiments that you can do to tell any different. If you drop an object in the car, it falls straight down in the car. For instance. And there's no other experiment. A pendulum would swing the same way, etc. There are no experiments that you can do to tell truly whether it's the car moving or whether you're in one of those like computer simulation rides that you see at some theme parks, where you're actually in an enclosed room and they just project hyper-realistic video of you moving down the road, and it really seems like you're moving down the road. So the person in the car is absolutely entitled to say that they are stationary and that the archer is moving to the left at 51 meters per second. In so doing, in the frame as we usually call it of the car, they see the arrow go straight up and down, but they would say that since the archer in their frame keeps moving further and further away from the path of the arrow, that this distance, call this x1, call that x2, this distance here keeps getting bigger and bigger. So they would conclude that the archer would see this parabolic trajectory that we've come to expect. So each of them is perfectly entitled to do physics within their own viewpoint, what we call a reference frame, and each of come up with an answer, and then they are perfectly capable of translating to what it is that the other observer will measure. So looking ahead to that thought, we can think about putting this a little more formally and thinking about what we call reference frames. So usually what we do is when we think of a reference frame, we think of just a coordinate system. You notice I'm drawing, I wrote a capital S there. That is the name of one of our observers conventionally. We usually call one of the observers S, and then we'll have another one. Oops, let me actually draw it like this. We'll have another observer that is moving with respect to S, and we'll call that observer S prime. And those are very standard names. And although each of them is perfectly entitled to say they're stationary and the other person's moving, usually the narrator in the problem is thinking of one of the observers as stationary. The one that the narrator thinks is stationary is S. So this is the one the narrator thinks is stationary. All right, let's say that our observer S prime, carrying their coordinate system with them, is moving at some velocity v, capital V here. So this is how fast this is the velocity that S prime is moving with respect to our observer S. Okay, now both of them can measure the coordinates of some object, and they will get different coordinates. And that's because S is going to be measuring from their origin and say that this position is R, and S prime is going to be measuring from their origin, and they're going to say that this position is R prime. And how it's going to differ is by the position that S measures, for S prime. I'll call that capital R. So following just like we've done before, we can see that this is by the tail to head rule. If I add R prime and big R, I get little r. So that's going to be our starting point. So the position that S measures will be the position that S prime measures plus the position of that S measures for S prime. Well, if we're moving at some constant velocity v with respect to S, that's going to work out to be plus the velocity of S prime with respect to S times the elapsed time. What I'm doing here is I'm assuming that the origins of the two observers' coordinate systems overlap at t equals 0. And if that's not the case, if the origins never overlap, or they do overlap but it's not t equals 0, it's pretty straightforward to make the little fudges that you need to fix that. You just add some constants into it. And it doesn't change the analysis any, so I'm just skipping that for convenience sake. Okay, so we can either say that the position that S measures is the position that S prime measures plus the velocity of S prime with respect to S times the time elapsed, or we can flip it around and get that the position that S prime measures is the position that S measures minus that same velocity times the time. And you will find that this is a general rule of thumb in these kind of things. This is technically what's called a Galilean transformation. And generally, when you have these kind of transformations, a good rule of thumb to remember how the equations work is change the primes, change the signs. Okay. Now, the big idea here is I can again differentiate both sides, or if you haven't had derivatives yet, it's the same limit taking process we've done before. And what I would conclude is that if I then, on top of this, I'm trying to measure the velocity of some object, say this is the velocity that S measures for it. We'll call that V because there's no prime to it. It'll turn out that this will be roughly the velocity that S prime would measure for the same object. And we get this by differentiating both of these with respect to time. If you haven't seen the derivatives yet, don't worry about it. It's not really important to what we're doing here. But the end result is that we can just add the velocities together. So the velocity that S measures will be the velocity that S prime measures plus the velocity that S measures for S prime, or again, change the primes, change the signs. So this is what gives us that whole thing where, say, if you're driving north on a road at 60 miles an hour and somebody's driving south on a road at 60 miles an hour, you can say you're approaching each other at 100 because that's exactly what you're doing. And you're saying, oh, this person's going at relative, the ground is relative to the ground. This person's moving at 60, but the ground is moving at 60, so that adds up to 120. That's the idea of these sorts of things. Probably worth just doing one quick semi-fleshed out example. So let's say you got something like in aviation, the fact, aircraft fly through the air, but the air is moving. That's the wind. And so they're very worried about what the ground track of the aircraft is. What is the velocity relative to the ground, since they're flying through air, but the air itself is moving. So let's say that we have an aircraft, flying like so. And relative to the air, we could say that our aircraft is going at 40 meters per second east. But then we can measure that the wind itself is blowing at 30 meters per second to the north. So what would an observer on the ground, what would an observer on the ground see? And I already messed this up because V here is the speed of the wind. So this is wind, air measured by ground. And then this is plane measured in air. So to get the velocity of the plane as measured on the ground, we would remember that v is equal to v prime plus capital V. So we can go ahead and let's do this one head to tail. So v prime is 40 meters per second. And we'll say that v, capital V here, is 30 meters per second to give me little v, the velocity that the ground measures for my aircraft. And by the Pythagorean theorem, this will work out to be 50 meters per second and an angle of 37 degrees north of east. And generally, that's how you do this sort of thing. I find it just easiest to just plain draw out the vector sum for these velocities for whatever it is the problem is asking for, rather than getting totally hung up on the equation itself. Alrighty, so in the next set of videos, we are going to start worrying about what happens if objects rotate. Catch you over there.